So now that we have an idea of a vector space, something that we can use linear algebra rules on, we want to talk about a basis. And there are more precise definitions of a basis about it has to span the space and be linearly independent, but I think it's more helpful to call it a coordinate system, and it's one of those things where you know it if you see it. There are some things about like if it's an over-complete basis, but that really only comes up if you get very deep into certain kinds of research. So I think it's more helpful to just say that it is basically a coordinate system, or I also like to call it an ingredient list. This is the list of all the essential things you have to mix together in some linear combination, and if you put these together in whatever combination, you can build whatever you want. It's kind of like your periodic table of whatever thing you're working in. So you've got the ones that you know, of course, from normal coordinates, x hat, y hat, z hat, but you also know that these are not always the best coordinates to use. And sometimes you want to use a different basis, like r hat, theta hat, and phi hat. These will accomplish different purposes. Different ones are suited for different problems. But here, I'm only talking about coordinates. We can just as well talk about functions. So I could have a basis for the functions I'm interested in. And that could be 1, x, x squared, x cubed, etc., etc. Now, this is an infinite dimensional basis. But if I add together 1, x, x squared, x cubed, in whatever combination, I can build out of Taylor series any analytic function that I am interested in. So we can build analytic functions out of what I will call a Taylor series basis. And analytic just means that there aren't any holes. There's nowhere where I divide by 0. There's no asymptotes. There are no hard corners where I can't take a derivative. Everything is just nice and smooth. And these are important because linear operators distribute, and this lets us be really efficient with our linear operators. So if I have some vector, I want to describe this in terms of coordinates, but now there's no guarantee that there's just 3 coordinates. If we're talking about functions, it takes infinitely many coordinates to describe your function. So we're going to go back to using summation notation and say that I'll have coordinate number I times basis vector number I. Again, the sum is implicit when this gets repeated. Now, when I have R as some linear operator, and let's say R is acting on my vector v, R is acting on this big sum. And the nice thing about R is that it distributes. So implicitly there's a sum, and each vi is a coefficient. These are just coefficients. These are your basis vectors. The coefficient just pulls out, because that is one of the things we assumed that a linear operator can do. So once I do that, I have this coefficient, the coordinate, times whatever the heck R does to my basis vector. So rather than every single vector I cook up being its own independent problem, all that I actually have to do is to see what R does on each one of the basis vectors. So there's this set list of things that I have to know. Once I know everything in that set list, that's it. I know what's going on. But let's make this a little more precise. So I already said that linear operators take vectors to vectors. So r times v, or r with v put in, is going to be a vector. And I would like part j of that vector. So I am asking this for coordinate j. I don't want to say coordinate I. I'm already using I here. And if I were to use I again, you'd get that mixed up, and you need to make sure to keep your indices separate. So for the result, I've got I am asking for part j of that. Now, vi is just a coefficient. That's just a normal number. It's not a vector. It's just a coefficient from the ingredient list. The e sub i's are the ingredients. So when this r acts on that vector, it makes a new vector. The vector is right here. So I want coordinate j of that vector. So I have v sub I times part j of whatever r is doing to basis vector number I. Now, this might start to look a little bit more familiar. So I am going to define right here that this is j comma I, part j of whatever r does to basis vector number I. So we write this like this. Now I have free indices. I have j. I'm talking about part j of the result. I'm asking for the jth coordinate, and that comes up right here. There's only one j on each side of the equation, and they match up. But here I have to do an implicit sum over part I of this matrixy thing and part I of that vector. So this is matrix multiplication. I could never remember matrix multiplication for the life of me when I first learned it, because it was some mindless algorithm. But it's not mindless. It's what the transformation does to every item in the basis. So if I'm going to write R as a matrix, the first column, because these represent, the J's represent rows, the I's represent columns. So everything that happens down the I, down the first column, is what R does to basis vector number 1. The next one is what R does to the basis vector number 2. Down the line to whatever R does to basis vector number n. And so the vectors get slotted in like that. And with this, we can build up whatever matrix we want and then just do the matrix mechanics we know. Better yet, you plug those into a computer, because that's what computers are made for. Do matrix mechanics, and your problem comes out. So the real challenge is taking whatever operation you want, picking the right basis for it, and then figuring out how to express that as a matrix. And we're going to do that now with some simple examples.